Welcome back to The Explainer. Today, we're diving into something absolutely wild. Literally, one of the most viscerally dramatic, tension-filled events in heavy industry. We're talking about the moment a brand new ship finally hits the water. It's a process steeped in history, calculated down to the absolute millimeter, and, well, packed with potential disaster. We're breaking down the traditional end launch. It's this incredible feat where a massive vessel goes from dry land to the sea, using nothing but gravity, precise engineering, and a surprising amount of grease. To really wrap your head around the gravity of this, literally, just picture the number 10,000. 10,000 tons of solid steel. That's the weight of a typical large hull, just sitting there on a slipway. Now imagine balancing all 10,000 tons of that steel on a lubricated track, totally stripping away the solid blocks that held it up for months and getting ready to just let it plunge into the water. We were talking about 60 seconds of controlled chaos. I mean, stop and think about the forces at play here. If the calculations are off by even a fraction, that 10,000-ton behemoth could crush its own supports or plummet catastrophically. The sheer scale of it is staggering.
So let's get right into Part 1, Anatomy of the Launch. Building from the ground up.
To understand how shipbuilders pull off this monumental task without sinking the ship before it even reaches the sea, we have to look at the structural breakdown. The foundation of the whole operation is the groundways. You can think of them as the launch rails. They're basically two parallel tracks, heavily reinforced, and built straight into the concrete surface of the slipway. They run all the way from the stern of the ship down into the water, inclined at this incredibly precise slope, typically 1 in 12 to 1 in 20. And that downward slope? That's what gives us the gravitational force needed to drive the launch. Gravity is absolutely the engine here.
But of course, gravity alone isn't going to cut it when you have 10,000 tons of steel grinding against a track, right? To overcome that massive coefficient of friction, the surface gets coated with a highly engineered lubricant mixture. Now, traditionally, shipbuilders actually used a mix of melted tallow and soft soap to minimize friction. Kind of crazy to think about. In modern applications, though, they've upgraded to specialized white metal lubricants. This drastically cuts down the friction, letting that massive ship actually start its slide down the ways.
So we actually have two main components at play. You've got the groundways, which we just talked about, static, fixed to the earth, angled down, and heavily greased, but resting directly on top of them are the sliding ways, and these are exactly what they sound like, the moving parts. They are attached directly to the ship, nested right on top of those greased groundways, and they bear the entire moving weight of the vessel. They form the base of the temporary launching cradle. So as the ship moves, the sliding ways travel right along with it, just gliding over those static groundways underneath.
Here is the catch, though. A ship's hull isn't perfectly flat. It has these fine, hydrodynamic curves, especially at the front and back. So how exactly do you sit a curvy ship on flat sliding ways? Well, you use poppets. Poppets are these temporary, super robust timber and steel support structures built specifically to match the curves of the hull at the bow and the stern. They bridge the gap between the ship's curved shell and the flat sliding ways below. And the forward poppet? It is absolutely critical. See, as the ship slides into the water and the stern starts to float, the whole ship will actually pivot right on these forward poppets. During that pivot, that forward poppet has to take up to 25% of the ship's entire weight. If it's a really fine-lined vessel, there's a very real danger of the bow just breaking right through them. So shipbuilders often have to fit temporary steel saddle plates or brackets right under the forefoot of the ship just to distribute that immense load safely.
Which brings us to Part 2, the countdown to chaos, transferring the weight.
Okay, so with the ways, the grease, and the poppets all set, the weight has to actually be transferred from those sturdy building blocks onto this precarious sliding cradle. And this is a highly procedural sequence that takes days. 4 days prior to the launch, a gang of workers uses long ramming poles to drive wedges into the launch blocks. They literally ram up the wedges to lift this 10,000-ton ship just a tiny bit, just enough to take the pressure off the building blocks. Then, 2 days before, they start removing the shores, the side supports. Fast forward to the morning of the launch, and the tension is really mounting. They knock out every second keel block. You can just imagine the vessel settling heavily onto the cradle. Finally, just 30 minutes prior, the last remaining keel and bilge blocks are pulled out. With every single block gone, the massive weight of the vessel is shifted entirely onto a sled sitting on grease on a downward slope, just waiting to slide.
And that takes us to Part 3, Triggers and Release, the final hold. At this exact moment, there are no shore connections. There are no building blocks. The entire cradle is loaded, and gravity is absolutely screaming to pull this ship down the slipway. So what on earth is stopping it? Well, it all comes down to the triggers. Back in the day, smaller ships might have been held back by just knocking away a wooden dogshore. But for modern, massive ships, we use electromechanical triggers. These things are a total marvel of engineering. They use a really clever system of mechanical reduction levers. This arrangement basically lets the crushing, gargantuan downward load of the ship be balanced by a relatively tiny releasing gear. And what holds that tiny gear in place? Solenoids, wired into a common electrical circuit. A simple electrical command, just reversing the current, releases catches that hold back 10,000 tons of steel. It is almost mind-boggling that such a small electrical mechanism is the only thing standing between a static ship and a completely violent launch.
This brings us to a really powerful quote from our source material. The full ship's weight comes on the triggers at the time planned for the launch. Read that again, and just imagine being the engineer in charge. The pre-launch checks are done. The surveyor confirms the cradle is seated perfectly under the hull. The grease crew has done their thing. Shore connections? Disconnected. The tugs are standing by in the water. Every single piece of wood and steel that held the ship safe on land for the past year is completely gone. The ship is practically trembling on the ways, 100% of its weight bearing down on those electromechanical triggers. The tension in the shipyard must be palpable.
And then the signal is given. The sponsor breaks the bottle. The electrical circuit is triggered. The solenoids snap back. The triggers release, and gravity instantly takes over. But the story does not end the moment the ship starts moving. Actually, the danger has just begun. What exactly happens to those 10,000 tons as they accelerate down the slipway over the next 60 seconds? How does the ship survive the violent transition from land to sea, the sudden onset of buoyancy lifting the stern, and that terrifying tipping moment where the whole vessel threatens to pivot catastrophically on its forward poppets? And once it's in the water, how do you even stop it? That single minute of physics in motion is the most dangerous moment in the entire life of the ship, and it leaves us with the ultimate question. How do we engineer survival when gravity and momentum take the wheel? Let that sink in.